Time now to discuss about electron configurations, and at this point we're going to understand how the electrons are organized within the empty space that is most of the volume of the atom. So to begin with, let's review what the quantum numbers are. So we have four, correct? We have the principal quantum number. It describes the main energy level. Then we have the angular momentum quantum number, which tells you the energy level, but most likely we refer to that number as describing the shape of the orbital. And then the magnetic quantum number gives the spatial orientation of the orbital. So in that empty space, what is the orientation? What point is that orbital directed to? So this, and then the last one is the spin quantum number that basically describes the electron. So the thing here is that the first three quantum numbers describe the orbital. So each one of those three, when you set a number for each one of those quantum numbers, the first three, you are specifying one single orbital. And within that orbital, then you can put so many electrons. Well, actually only two. But then once you have defined what the orbital is, then the spin quantum number then describes what the electron is doing in that orbital. So let's talk a little more about that spin, because we were saying that the electrons will spin one way or the other, right? So it doesn't matter in which way, it's just that they spin one way and in the opposite way. That's why you have a positive value and a negative value, and that's just a convention. Okay? They are all have the same spin, that's why it's only two values, positive or negative, depending on the direction of the spin. And all we want to do is to be able to describe how those electrons are occupying every single orbital. And for that purpose, we use an orbital diagram, which is pretty much a box. And each box represents one single orbital. In this particular one, we have the 1s orbital, and there is only one electron inside that orbital. And the electrons are represented with arrows. Arrows pointing up, arrows pointing down, depending on what value of the spin quantum number you use for that particular electron. So what we want to do is just to describe how those electrons are distributed on that atom using these diagrams, right? So one of the things that we were discussing last time was that not two electrons, if you have any two electrons in the atom, they must be different in at least one of the quantum numbers. So all four, remember, you will have N, L, ML, and MS. Two electrons cannot have exactly the same four quantum numbers. They have to differ in at least one of them. That means, remember, if the first three define an orbital, then if you put two electrons there in that orbital, then they at least have to differ in the spin, plus 1/2 or minus 1/2, but you only have two values there. Then, therefore, you can only put two electrons in an orbital, because then, if not, then you're going to have repeated numbers. Okay, so for example, we're going to look here at the configuration of helium, and helium is just two electrons, right? So for helium, it's simply the 1s orbital with two electrons in there. Okay, so the electron pointing up will have a spin plus 1/2. The electron, the arrow pointing down would be the spin minus 1/2. Think about putting another electron here. If you put another electron, let's say pointing up, that is going to be also plus 1/2. This 1s orbital here already has n equal 1, L equals 0, and ML equals 0. So those three numbers are already defined. Adding another electron will give you plus 1/2. You already have plus 1/2 there. So this is not possible. You cannot add a third electron there, not pointing up, not pointing down, not pointing left, not pointing right, for that matter. Okay, so they can only point up and down. So it's not possible. And that is what we know as the Pauli exclusion principle. And in the simplest way to express it is that no two electrons can have the 4 quantum numbers the same. Okay, that's pretty simple. So now, how do we use these quantum numbers and electron configurations? So every single electron in an atom will have a set of 4 quantum numbers. Okay, and that will describe where in the atom that electron is located, where including how far or how close that electron is to the nucleus. Okay, once again, the first 3 give the location, gives what is the orbital that an electron is occupying, and the 4th, the spin number, will give you whether that's pointing out or pointing down. It's a little inconsequential, so you don't have to worry too much about it. It's just a number that you use to describe the electron that is occupying that particular orbital. Okay? So we have this set 1, 0, 0 plus 1/2. So remember, this is N, L, ML, and MS. And this, the MS value, the only difference is the MS value, that is minus 1/2. These 2 electrons, this is electron 1 and electron 2. These 3 numbers are the same, therefore is the same orbital. So these 2 electrons are in the same orbital. Okay, and that's pretty much, this is helium. The 2 electrons in helium will be occupying a 1s orbital, and those 2 electrons will be together in that orbital. So what is the electron configuration then? The electron configuration is just, you can see it as a list of where every single electron of a particular atom is located in terms of the orbitals that they are located in. Okay, so this should be familiar to you, the ground state. For the case of helium, not helium, hydrogen, when we were discussing the Bohr model, the ground state was the lowest energy level, correct? So depending on where those orbitals are located, they will be higher or lower in energy. Remember, what does that depend on? Depends on the value of the principal quantum number. The higher the value of the principal quantum number, the higher the energy of that particular orbital. So let's put it this way. If you compare a 1s orbital with a 4s orbital, then the 4s orbital is higher in energy because it belongs to a higher energy level. How do you know that it belongs to a higher energy level? Because N equals 4 in that case, and in this case N equals 1. So N is larger in the 4s. That means that is a higher energy orbital. That's pretty much. So if you were to put an electron in one of these orbitals, you will go first with the 1s. Why? Because it's lower in energy. So when you are distributing those electrons, you are trying to acquire the lowest possible energy on that configuration. That one, we will call it the ground state, and only the lowest energy orbitals will be filled. Okay, so that's what we are looking for in this electron configuration. So for example, helium, this is the information that we are looking for. Helium is 1s2, right? That means that number that we have here as a superscript, that is the number of electrons that you have in that orbital, in that subshell. Okay, of course the s indicates what the shell is. This is an s orbital, and it's an s orbital that belongs to the first energy level that is described by excuse me, n equal 1. Okay, so that's what we are aiming for, to write that electron configuration on those terms. Not necessarily in terms of the box, but at some point we start with the boxes and then we end up just writing that electron configuration. So oxygen will look something like this. You have basically 2 electrons in a 1s orbital, 2 electrons in a 2s orbital, and 4 electrons in a 2p orbital. And you may be thinking, well, but didn't you say that you can only put 2 electrons in an orbital? Yes, I said that. But you have to remember that if you are looking at the s orbital, the s orbital is just one orbital. However, the p orbital is actually three different orbitals, okay? Because remember, this is ml equal -1, 0, and +1. So that originates three different p orbitals, but they are the same energy. So you have to be careful with that too, right? They are different, so they are three individual p orbitals that if they are in the same energy level, all those three will have exactly the same amount of energy. And each one will have a capacity of 2 electrons, so a p orbital can actually hold 6 electrons. Okay, so there is nothing to worry about here. You have 4 electrons there in the p orbital. You can accommodate up to 6 in a p orbital. So that's the electron configuration for oxygen. If you look at iron, iron would look something like that. Okay, don't worry too much about right now. We're gonna get to the point in which we're gonna be able to write these electron configurations. But the point is, this is the format that you will be seeing. Okay, you are indicating what orbitals and how many electrons in each orbital. So that's what we are looking for here. Okay, that's the purpose of the electron configuration. So let's take a look at a few electron configurations. So we already know hydrogen and helium, right? So it's just the 1s orbital. For hydrogen, only 1 electron. Well, you don't have any more, so you just put 1 electron in the 1s orbital. For helium, you have 2 electrons. Those go into the 1s orbital. So now lithium. Remember, for lithium, Z equals 3. Okay, so you have 3 electrons there. You can only put 2 in the 1s orbital. So once you put 2, you still have 1 more to go. So you have to put that in the next available orbital, the next lowest energy orbital, and that is the 2s. So you put that next electron there. For beryllium, which is Z equals 4, then you have 2 that you put in the 1s orbital, and then you are left with 2 that will go. Do you still have room in the 2s orbital? Okay, from lithium to beryllium, it's just you are adding 1 more electron. There is still room in the 2s orbital to put that electron. Once you run out of space in these s orbitals, then you have to move into the p orbitals. Okay? So for boron, which is Z equal 5, then you put the 2 in the 1s, 2 in the 2s, only 1 more electron to go, that goes in the p orbital. Okay? For carbon, carbon actually presents an interesting story here. So carbon, Z equals 6, you have to distribute 6 electrons. Now you have 3 rooms here, correct? So you have 3 p orbitals and you have 2 electrons to put there. So you might be thinking, okay, I have 2 electrons, I have 3 rooms in which we can put the electrons. Why am I putting those electrons in separate rooms if you can perfectly, well, I'm going a little ahead of myself here. So let's continue with carbon here. So why did you put those 2 electrons in separate rooms when you have, let's say, you can put them in the same room, right? So now that doesn't happen. Those electrons, remember, what are electrons? Electrons are negative charges, correct? So if you put electrons in the same room, naturally they're gonna repel each other. So they are negative charges, they are moving really fast. If you put them in the same room, in the same space, in the same region in space within that atom, then there's gonna be more repulsion. So do you want to minimize that repulsion? So those electrons don't really like each other that much. So they prefer, they don't want to be in the same room if they can help it. Okay? So that's why for carbon, you would have those 2 electrons not occupying the same orbital, the same single orbital, but occupying different p orbitals. Okay, so if you have the room, you do it. So that happens with nitrogen as well. you have 3 electrons, you don't put 2 in the same room unless you have to. Okay, so with nitrogen, you still can afford to put 1 electron in their separate room. When you go to oxygen, then there is no other choice. Okay, if you start putting 3 electrons and you put it in 3 different rooms, you still have 1 more electron to go. For that electron, there is no other choice but occupy one of the rooms that already have an electron there. That is still the lowest energy configuration, because if that electron wants their own room, then it has to go to a higher energy level, and there is a cost associated with that, so they don't do it. So same thing for fluorine here. Okay, you have 2 extra electrons there, no choice but to put it in a room already occupied. And when you get to neon, that Z equals 10, well, you have a full house there. Okay, all electrons are, all orbitals are full. They are a maximum capacity, and the capacity for one single orbital is always 2 electrons. That's the maximum number of electrons that you can put in a single orbital. Now, that thing that we were doing, if you have the space, you put those electrons in separate rooms, it has a name. So that's what we call the Hund's rule. And the Hund's rule simply tells you that the electron configuration, or the lowest energy electron configuration, is when you have electrons on pair. Okay? So when those electrons, like here, that electron is by itself, there is nothing else with that electron there, that electron is unpaired. Okay? Now, electrons that are together in the same orbital, remember it's just 2, the maximum occupancy is 2, these are paired electrons. Okay? So here the Hund's rule tells you that you want to have, for any electron configuration, you want the maximum number of unpaired electrons. Okay? So that means that you will not complete, like in the case of carbon, you will not put an electron here if you still have room, empty rooms, let's put it that way. Okay? You will not fill an orbital, and remember, this has to do with the same type of orbital. So you have 3p orbitals. You cannot completely fill one of those p orbitals if you still have unoccupied p orbitals. That goes for the d orbitals as well. You have 5 different d orbitals. You cannot fill one single d orbital if you still have empty d orbitals. So for any particular kind of orbital, that holds true. So you don't fill them, you don't completely fill them if you still have room in those subshells. Okay, so this is what it looks for each one of these elements. Now, if we pay a little attention, if we focus our attention on nitrogen, oxygen, fluorine, and neon now, well, we can see that, for example, nitrogen, oxygen, and fluorine, you will see that there is at least 1 unpaired electron. So for nitrogen is 3 unpaired electrons, for oxygen is 2 unpaired electrons, and for fluorine is 1 unpaired electron. When you go to neon, there is 0. There are no unpaired electrons. All electrons for neon are paired. And that gives a particular property to these elements. So whenever you have unpaired electrons, we associate that with paramagnetic character for that material. Paramagnetic meaning it will respond to magnetic field. So think about you have a magnet, and then you put that magnet close to nitrogen, let's say, and it will be attracted to the if you have that nitrogen atom, that nitrogen atom will be attracted to the magnet, so it will respond to that magnetic field. But neon, in contrast, because all electrons are paired, is going to be diamagnetic. And diamagnetic means it will not respond to a magnetic field. So you can put the magnet close to the to a gas molecules of neon, and nothing is going to happen. It will not be attracted. So that is the main difference. Okay, paramagnetic and diamagnetic. Paramagnetic require the presence of unpaired electrons, and just one will do. So even if you just have only one unpaired electron, that will give paramagnetic properties to that particular element. And well, if you have more, the paramagnetic character, you can also see it from the point of view that the more unpaired electrons that you have, well, it would be even more attracted to, it will respond more strongly to magnetic fields, but you don't really have to worry about that. So it's just, as of now, all we want to know is that whether it's going to respond to a magnetic field, and if you have unpaired electrons, that will happen. It will, that element, if it has unpaired electrons, it will respond to magnetic fields. Now, how do we do this electron configuration? So we use the Aufbau principle. And the Aufbau principle, pretty much the meaning behind this, it's just a fancy name to describe what is going on. If we want to translate what this means, it's just go from lower energy, to higher energy. So you're going to start with the orbitals of lower energy, and then you're going to feel, technically it's like you're going to fill up according to the energy. However, I have it easier to picture if I draw like this. And this is basically the Aufbau diagram that I usually use to teach this. Okay, so this is N, and here we have 1, 2, 3, 4, 5, 6, and 7. Okay, so then L goes in this direction. This is 0, 1, 2, and 3. And remember, 0 is S, 1 is P, 2 is D, and 3 is F. And that describes like sort of a matrix in which you are going to locate those electrons. Remember, maximum occupancy for a s orbital is 2, so you can only put a maximum of 2 electrons there. For a p orbital, remember there are 3 p orbitals, so you can put 6 electrons there. For a d orbital, you have a total of 5 d orbitals at every level, so that's 10 electrons. And for an f orbital, you can put 14 electrons. So that's a total of 7 f orbitals, so a total of 14 electrons that you can locate there. So how do we actually use this diagram? So let's think about argon, for example. And argon has 18 electrons. How do we do this distribution for argon? So we use our diagram, our Aufbau diagram. And all you do, technically, I would like to see it as following the arrows. So you go to the next available arrow, so to speak. So if we start for argon, we have, you put 2 electrons there. The next available arrow is the 2s, so 2 more there. You are with 4 electrons there. So you put 6 here on P. You are at 10 right now. Let's do it this way. You have done 2, 2, and 6, that's 10. 2 more in the 3s, that's 12. And if you are at 12 right here, then you need 6 more. Okay, 6 more to go. Well, they'll go here. You can put those 6 electrons there. So technically the configuration of argon would be 1s2, 2s2, 2p6, 3s2, and 3p6. Okay, so this would be the electron configuration. And one thing that I want you to keep in mind is that the way we are going to use this in this class is that you are going to write the configuration in the order in which you are feeling. Okay, so that is going to make more sense in a little bit. So that's the configuration for argon. So 1s2, 2s2, 2p6, 3s2, 3p6. Now, what if we want to do the configuration of calcium? And well, you're gonna say, well, it's Z equals 20. So technically it's the same configuration of argon, So 2, 2, 6, 2, 6. Okay, at this point, you have 18 electrons. The next arrow is this one over here for the 4s. You are not going to the 3d, you are going to the 4x because it's the next arrow, and you put those 2 electrons there. Okay, 18, it's 20 electrons that you need, just 2 more, you put those on the 4s orbital. That is the configuration of calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. It's really important that you remember that that electron goes, those 2 extra electrons go to the 4s and not the 3d. And why is that? Well, even if the 3d belongs to a lower energy level compared to the 4s, if you look at the actual energy contained of that orbital, well, the 4s is actually a little smaller, a little lower energy than the 3d, and therefore it sort of cheats a little bit and cuts in line, and then those electrons go there instead of the 3d. You can see it from the point of view that it energetically is more favorable to put those electrons in the 4s than in the 3d, even if the 4s belongs to a higher energy level. Okay, so but here, one thing that I want you to notice here is that let's take a look at that configuration of calcium, right? So if you look at this part, the one that is in blue, okay, and then you look at the argon configuration, well, it looks like they are the same, right? So because of that, and remember, these are for energy levels, right? So the highest energy level in calcium is the 4th level. That means that anything below that energy level is what we call core electrons, and most likely that resembles the configuration of argon. Okay, so those that are in the highest energy level are what we call the valence electrons. Okay, and there might be a little difference there for transition metals. Transition metals are a kind of a special case, but for the most part, the highest energy level contains the valence electrons, and anything below is considered a core electron. And that whole configuration of the core electron, usually we represent it as a configuration of a noble gas. Okay, noble gas are also special in their very own way. So we can rewrite the configuration of calcium as simply argon 4s2. Okay, up to that point, up to the first 18 electrons in calcium, the configuration is exactly the same as argon. So we use that as a shortcut, and we call this the shorthand notation. Okay, this one is your full configuration, and when you put the noble gas within brackets, then that is the shorthand notation. Now, what if we start complicating this a little more? Okay, now this vanadium, we are just adding 3 electrons to what calcium was, right? So we have 2, 2, 6, 2, 6. Up to this point is argon. If we add 2 here, then that's calcium. We are at 20 right there. The next available arrow is the 3D. Okay? At this point, you have 20 electrons. You need 23, so you add 3 here at the orbital. Okay? Therefore, the configuration of vanadium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Okay? Now, remember, I told you to write the configuration the way you are filling the orbitals. That means that 4s orbital is filling up before the 3d, therefore you write it first in the electron configuration. There are books in which they don't do that. You go just by level, but for this class, you are going to write it in the order that you are filling them. Okay? So now one thing that you notice is that the last orbital that you are filling here is a d orbital. Okay? And that's a characteristic of transition metals, but more on that later. If we use the shorthand notation, this here, up to this point, that is the argon configuration. So we use the shorthand version here, argon, then the 4s2, 3d3. Technically, for transition metals, these are your core electrons. Okay? So pretty much you can consider, and I would suggest you just keep that for transition metals. Main group, it's a different story. For transition metals, anything that is kind of out of the noble gas configuration, you can consider that. Why did I put core there? This is not core. They are not core electrons. They are balanced electrons. Okay? Now, if we do chromium, chromium is just one more electron, right? So therefore, if you just, instead of adding 3 to the d orbital, then you add 4. So you end up with this 4 right here. Now, chromium presents a particular situation because if you think about it, the d orbitals, the 3d orbitals, they are 5, right? Excuse me. So that means you're putting 1, 2, 3, and 4 electrons there. And then you have this orbital here, very sad, unoccupied, and that orbital is actually not happy about it, okay? So whenever you have this situation in which you end up, and this goes for transition metals, if you finish your d orbital in a 4, well, this orbital here, hey, I want an electron really bad, so I don't know what you're gonna do, but you're gonna give me an electron. So you put one electron here, and where do you get that electron from? You get it from the s orbital. So you take one of these s orbital electrons and you send it to the last d orbital there, because that d orbital really wants that electron. Okay, he doesn't want to be abandoned, like the other 4 have electrons, why I don't have one? So the actual electron configuration for chromium is not this one in which you end up with d4, but one in which you have d5. Okay, you take one electron from the s orbital and then you put it on the d5. The shorthand notation would be argon, because that's what you get up to this point, plus whatever is after the configuration of argon. Remember, these are your core electrons and these are your balanced electrons. And whenever you do this, if you end up with 4 in a d orbital, that is what we call d4, and also happens with d9. If you end up with 4 or 9, these are d4 or d9 exceptions. So it will happen that a particular element, if the last orbital that you are filling is a d orbital and you end up with 4 or 9 in that configuration, they are going to pull one electron from the previous s orbital, and then they're going to complete either one electron in each room for the d4, so that it becomes d5, or complete 10 electrons from the d9 to have all the d subshell full. Okay, so that's what they want to do. And this electron configuration now allows us to classify these elements, okay? Because according to the electron configuration, now we can say, well, the main group elements are those that the last electron is going to an s or p orbital. The transition elements, well, they are basically metals, all of them. the last electron for a transition metal goes into a d orbital, and the inner transition elements, the actinides and the lanthanides, the last electron is going to an f orbital. Okay, so now you can classify elements according to the electron configuration, just remembering where that electron, the last electron that you are putting in that configuration, where it goes. Okay, and pretty much that also tells you what electrons you can consider for valence electrons. So for example, for a main group, because the last electron is added to an s or p orbital, those are the only ones that you consider as valence electrons. Okay, so main group is the valence electrons are in s and p orbitals. Okay, but for transition elements, you also count the d orbitals, the d electrons. Okay, and technically for a inner transition element, you should count also the f orbitals, but since it gets more complicated, well, we don't want you to make your life even more difficult, so you don't have to worry about the f orbitals for now. Okay, so just worry about sp and d when it comes to valence electrons, and you will be fine. Okay, so the bottom line is that the valence shell, the valence electrons, are the highest energy electrons in the electron configuration. And how do you know that? Because they usually will go into the highest energy orbitals. Now, this is a periodic table in which you have every sort of electron configuration, and you don't have to memorize all of that. Yeah, you can even have it by your side. But the thing is, I want you to notice that in this periodic table is that if you take a look at this, basically, this periodic table is telling you where the last electron is being added. So the last electron in groups 1 and 2 go to an s orbital. So now we can divide the periodic table according to what is going on here with electron configurations. Since in these two groups the last electron goes into an s orbital, this is what we call the s block. Now we take a look at this, kind of the side of the nonmetals. Now the last orbital, the last electron is going into, let's put a little bigger, into a p. So the last orbital being filled here is a p orbital, so this is a p block. Right down the middle, what you see here is that the last electron is being added to a d orbital, so consequently this is a d block. And down here in the rare earth, the lanthanides and the actinides, the last electron is going into an f orbital, so this is an f block. Okay, and why is it convenient that you remember all of this? Because then you don't really have to worry about counting electrons when doing electron configurations, because this is giving you a pretty quick way to do electron configurations. What do I mean by that? So let's say, for example, you want to do the electron configuration of strontium, okay? And strontium is 38 electrons. Well, you can do shorthand notation, right? So basically it's the previous noble gas. At some point, there is part of this configuration that is going to look like a noble gas. Well, if it's strontium, what is the previous noble gas? The previous noble gas is the largest noble gas that has an atomic number lower than strontium. So if it's 38, then the noble gases that we have here, well, 54, xenon 54 doesn't do because it has an atomic number larger than strontium. But then we have krypton that is 36. So krypton is 36. So strontium is going to be equal to krypton, and you have 2 more electrons to go. where does the 2 electron go? So strontium is in the 5th period, so it's 5s2. Did you actually have to do the Aufbau principle to do the electron configuration? No. If you can get away with the shorthand notation, by all means do it. Okay? If you are not completely convinced, how about we do nickel? And nickel is 28. Okay? So let's, before we get there. That's not what I want to do. Yes. If we do nickel, right? Now nickel is 28. The previous noble gas for nickel is argon. Okay, argon is 18. So nickel is going to be equal to argon. 28 minus 18, 10 electrons to go. Okay, the first one, to get to nickel, you have to cross the 4th period. So you get the 4s, and you can only put 2 there. So 10 electrons, you use 2, you have 8 more, and then you move into the D block. Now the D block, you have to be careful, because when it comes to blocks, it's going to be the NS, the NP, but the N minus 1 D. You have to be careful with that. In any given period, if this is N, if this is 4, when you go into the D block, is N minus 1. So this is a 3D8. Okay, which is what you have there. Okay, so that is the kind of the shortcut to do electron configurations. Get very familiar with the periodic table in terms of these blocks. It's gonna allow you to do electron configurations really, really quick. Okay. Now, when it comes to noble gases, these are the atomic numbers for each one of those. If you want to look at the configuration of the noble gases, then we are looking at something like this. And of course, they are noble gases. We can also do the electron configuration of the noble gases using shorthand notation. And this is what we have, right? So one thing that, this is a 2 right there. One thing that you notice here is that for those noble gases, some of the properties include that they are monatomic gases. For example, helium is going to be just the atomic helium. If you compare helium to hydrogen, well, hydrogen exists as a diatomic molecule. So helium exists as a monatomic gas. And they are fairly non-reactive. They don't, I don't know how to put it. They just are prone to reaction. Does that mean you can actually not make it participate in reactions? Well, actually you can. There are few elements in the periodic table that will make those noble gases participate in reactions, but they are not very comfortable doing that. So, and because in the chemical reactions electrons are involved, they have very low tendency to lose or gain electrons, so they don't want to do that. So if we take a closer look to these noble gas configurations, we will notice that that last shell, the highest energy level that you have in each of the noble gases, except for helium, they all complete 8 electrons in the last shell, okay, in the last level. So you have 8 electrons here, you have 8 electrons here. If you consider only the level 4 electrons, then there is 8 here, same here, and same here, except for helium. For helium, you just count 2 because there is no more electrons there. But for every other single noble gas, they complete 8 electrons in the last shell. And that is associated with great stability, okay? So having those 8 electrons in the last shell is assumed to give a very stable level to any atom, and that's why pretty much every element in the periodic table wants to be like a noble gas. They want to complete 8 electrons in the last shell, and they would do that by any means that they can. That's why they will be losing electrons or gaining electrons depending on how far they are for that noble gas configuration. They acquire, or they reach those 8 electrons in the last shell, they acquire stability and they are happy. That's what they want to do. So now if we look at configurations of ions, for example, for calcium, C is equal 20. So now, one of the things that you remember is that calcium always works with a charge of +2. So that means it has only 18 electrons. So if you are to take electrons from calcium, where do you take them from? You take them from that last level, the highest energy level that is filled. That's usually where you are going to take those electrons. Okay? Now, if you write the shorthand notation here, before we got there, now with those 2 electrons gone, there is no more the 4th layer of electrons there. Now you go down to the 3rd, and in this 3rd layer you have 8 electrons. Moreover, when you write the whole shorthand notation, the configuration, the electron configuration of the calcium 2+ ion is that of argon. So the calcium 2+ actually looks like a noble gas, and it's very stable. So the calcium 2+ ion, calcium 2+, let's put it a different way. Calcium always wants to work with 2+ because it gives it configuration of noble gas. Okay, simply put. For oxygen, now we have O2-. What do we do there? So oxygen, this is the last shell for oxygen, right? And it's gaining 2 electrons. What do you do there? So you have to add those 2 electrons, right? O2- means you have 10 electrons. What do you do with those 2 extra electrons? Well, you put it where do you have room. So the p orbital can hold up to 6 electrons. You only have 4 there. You can add those 2 to the configuration of oxygen. And guess what? Here now you have 8 electrons in the last shell. And that configuration, 1s2, 2s2, 2p6, is a configuration of neon. So O2- has the electron configuration of neon. It looks like a noble gas. The O2- ion looks like a noble gas. That's why oxygen likes to work with 2-. Okay? So in general, those were just 2 examples. You take electrons from the highest energy level, or you add electrons to the highest energy orbital that still have room to hold those electrons. So for anions, you are adding electrons. So sulfur here, okay? Sulfur 2-, you just added 2 electrons there, okay? So all you did here was to add 2 electrons there. So now you have 3s2, 3p6. You have 8 electrons here now. And that configuration, if the neutral atom has that configuration, the shorthand notation, now S2- is equal to argon. Okay, you are moving to the next noble gas. For cations, then you start again with your neutral atom, and then you take electrons out of that, the largest orbital, the highest energy orbital. Now, one thing that we need to be clear here, okay? So for barium 2+, you will take this electron here. Okay, so that 6s orbital will be gone because it's going to be empty. So if it's empty, you just don't write it for the configuration. And effectively, barium 2+ will have the configuration of xenon. Now, Sn4+, this is the configuration. For Sn4+, you take from the highest energy level, no matter what. So the highest energy is 5. So you are taking those electrons from the p orbital and the s orbital, but you don't touch the d orbital. Well, you don't touch it unless it is necessary. So the electron configuration of SN4 is going to be krypton 4d10. Not exactly a noble gas configuration, but all of your orbitals are 4. Okay? So all I want you to keep in mind is that when you are taking electrons to form a cation, first you go to the NP first, then you move into the NS, and last, if you still need to take electrons out to form the cation, then you go to the N-1D. That is the order. Okay, so for example, if you were doing SN 2+, okay, you will only take the 5p. So this will be krypton 5s2 4d10. Okay, and hypothetically, if you were doing, let's put it this way, SN 6+, then you take the 5p, you take the 5s, and then you take 2 from the D. It's going to be equal to krypton 4d8. Okay, so this is the order: first, second, and last. Okay, do not forget that. So now we are able to understand a little more about the elements in the periodic table. So we have the alkali metals. They are all have one more electron than the previous noble gas. So all they have to do is to lose one electron, and then they acquire noble gas configuration. That's why group 1 metals always work with 1+. They lose that electron, they have noble gas configuration. In the other hand, the halogens, they are just one electron away from the noble gas configuration. All they have to do is to gain one electron. That's why halogens always want to work with 1-. Okay, gaining that extra electron puts them in configuration of the next noble gas. That's why they want to, they want that electron, that extra electron, so badly. Okay, so that's why the halogens, when participating in reactions, will tend to gain electrons, and the group 1 metals, and metals in general, would want to lose electrons. Okay, so if you put all that together, the group 1 metal, they want to lose that electron really, really bad, and the halogens want to gain an electron really, really bad. That makes them the most reactive groups in the periodic table. It's just one electron. It's one electron losing or one electron gaining. Then they are very reactive for that reason. It's very easy for them to either lose an electron or gain an electron depending on the group that you are. Okay, so once again, group 1 metals are the most reactive metals. Halogens are the most reactive non-metals. Okay, so this is our first step to understand why elements behave the way they do. This is just a glimpse. This is just the beginning. The next part is going to be periodic properties, and then you will have a better understanding of, in general, around the periodic table, how the elements behave when it comes to reactivity. Okay?